In this lesson, we will discuss a probabilistic clustering model called the Gaussian Mixture Models GMM. We will start by explaining the differences between soft clustering and hard clustering and why soft clustering is needed. Then we will discuss the Gaussian Mixture Models clustering, which involves the expectation-maximization algorithm. Finally, we wrap up with strengths, limitations, and takeaways. In hard clustering, every point belongs to one cluster. Now consider a dataset that is not clearly separable into three disjoint groups. It looks like there are dense regions around the cluster centers, but there are also points located in the boundaries that may belong to one cluster or another cluster at the same time. For example, think about someone sitting here who watches football games and basketball games. So this person can belong to two clusters with different probabilities. The notion of soft clustering is that every object is assigned to one cluster J with a probability. Formally, the probability of a hidden variable called Zi equals to cluster J, and the sum of all probabilities equals 1. Clearly, soft clustering offers more flexibility over hard clustering because a data point can belong to more than one cluster with different probabilities. Let's take a moment and go over some of the assumptions a Gaussian model makes. Basically, we are going to assume that the dataset was generated by sampling from k Gaussians. At the beginning, we don't know the value of the parameters of these Gaussians, specifically the mu and the sigma or covariance for higher dimensions. We also don't know the mixing proportions. In other words, what fraction of the data comes from each Gaussian. For example, maybe it's 30% from the first one, 50% from the second one, and 20% from the third. To summarize, it looks like there are two things we need to learn from the data. First, for each cluster, we need to estimate its mean and deviation. Second, the probability of soft clustering. In other words, how likely is that a randomly chosen data point was generated by that Gaussian? The key idea in soft clustering is to compute the membership probability of xi belonging to a cluster Cj. For a data point xi, that membership probability that it belongs to Cj is expressed as the posterior probability of Zi equals Cj given xi, which we can compute using Bayes' rule. The first term is the prior probability of the cluster. In other words, what fraction of the data we expect to come from that cluster even before seeing this point. And the second term is the likelihood. Given that xi belongs to Cj, what is the probability of observing its features? In GMM, the likelihood comes from a Gaussian with a mean and a standard deviation. So as a result, when we multiply the prior and the likelihood, we get a score for each cluster that is normalized to the probability of soft clustering. Now the problem is formulated as how to compute soft clustering. To compute these soft clusterings, we need the cluster prior and parameters, but at the same time, we can't reliably estimate these parameters without knowing this membership probabilities. That's why we are going to use the expectation maximization algorithm. Briefly, Maximum likelihood is a principle for estimating model parameters by choosing the values that make the observed data most probable under the model. First, we randomly initialize the parameters, which are the means, standard deviations, and prior probabilities, because we don't know the true means, covariances, and priors. We have to start with random values. Now, in the E step, that we have some initial guesses, we can compute the posterior probabilities for each data point by multiplying the prior by the likelihood, which is the probability of xi given its cluster Cj and the initial parameters theta. The result of the E step is a soft membership to each data point in each cluster on the current guesses. Next is the M step. Using these posterior probabilities, we update the model parameters by maximizing the likelihood or the log likelihood. Now we have to compute more precise estimates for the cluster mean, standard deviation, and prior probabilities because we started with initial guesses which may not be very accurate. So as you can see, there are double summations here. So this process is iterative until convergence, where soft assignment and model parameters are no longer changing. In summary, the M step chooses parameters that maximize the likelihood, where each data point contributes to each Gaussian in proportion to its responsibility computed in the E step. Let's walk through an example to show how the EM algorithm works. Suppose our dataset consists of 4 data points, 1, 2, 4, 5. K, the number of clusters equals 2. In the initialization step, we give initial values for mu, sigma, and a prior probability for each cluster. Then in the E step, we evaluate the soft clustering using those initial values. To compute the likelihood, we are going to use a Gaussian, a probability density function. So to obtain probability of xi equals 1, mu equals 1, and sigma equals 1, plug in the values into the formula and get 0.3989, and do the same for the remaining values. Next, as you can see here, I summed across clusters, so I got the denom value, then put the formula together and got the soft clustering for those initial values. And at this point, we are done with the E step. In the M step, we are going to find the parameters mu and sigma that maximize the likelihood or the log likelihood. The mean of each Gaussian is a weighted average of the data points multiplied by the weights, which is determined by the membership. The covariance measures the weighted spread of the data around the mean, and the membership probability or the mixing probability is the fraction of the dataset explained by the Gaussian computed as the total membership assigned to it. Here are the concrete values for mu's, sigmas, and prior probabilities for each cluster. And as you can see, the result of the second iteration, now we are confident that 0.1 is assigned to the first cluster, 5 to the second cluster, and see how the points started to converge. So 0.2 is 0.9999 and 0.4 here is also 999. One more iteration and the algorithm converged and we have the final clusterings. This example shows how the EM algorithm fits a two-dimensional Gaussian mixture model. We start with unlabeled data and an initial guess for Gaussian parameters. The circles indicate the initial component locations. In the E step, we compute soft clustering, which is the probabilities each point belongs to each cluster. This is why the points are colored gradually. The solid red or the solid blue indicates that this data point belongs to this cluster with a higher probability. In the M step, we update the mean and covariance matrices using soft clustering, and the ellipses show how the Gaussian components after each iteration. As we repeat the EM here at L2, 5, all the way to 20, the Gaussians move, rotate, and reshape to match the data. By convergence, each Gaussian captures one cluster. Here is another visualization, shows how the shape of a Gaussian change over iterations until convergence. Strengths of Gaussian mixture models. First, mixture models are more general than simple partitioning methods like k-means. They can represent clusters with different sizes and densities. Each cluster is described using a small number of parameters, its mean, covariance, and mixing weights. Finally, GMMs are generative models, meaning the fitted results align very well with probabilistic and statistical modeling assumptions. There are also several important limitations. EM can converge to a local optimum, so results depend on initialization. In practice, this is often handled by running the algorithm multiple times with different random starts. GMMs are computationally more expensive than k-means, especially for high dimensions. Choosing the number of clusters is also challenging and usually requires model selection techniques. Finally, depending on the covariance assumptions, the model may be limited in shapes of clusters it can represent. In summary, we discussed a probabilistic clustering model called the Gaussian Mixture Model. In this lesson, we will discuss a probabilistic cluster model called the Gaussian Mixture Models.